evening, everyone. Am I audible? Okay, so today we have with us Adrish Dey. He is an independent researcher and a Google Summer of Code Scholar 2019. And today's session is based on a research paper done by him. So, over to you, Adrish Dey.
Yeah, sure. Hi. Am I audible or do I
Yeah,
have to
yeah,
change some?
yeah, you're audible.
Just just give me a moment. I think I'm hearing some echo. One sec. Uh, okay. I don't know. Sure. Okay. So I think right. Give me a moment. Okay. So hi, I'm Adrish, and I'm a senior year undergrad at Netaji Subhash Engineering College. And I'm mostly an independent researcher working in the area of manifold learning, generative models, and topological data analysis. So one of the things which I want to share with you guys today is why we should care about topology and why is there so much why do people care about topology so much. So that's the session. So today's session is all about that, about topology and why should we care about it. And at the end, I'll be sharing some information about my recent paper on Topo Sampler, a topology constrained noise sampling in GANs. I'll be providing some insights of what we found and why we should care about topology more. So I think I should start with my slides. Uh, sure. So, what are the key takeaways for today? So the first thing that I want to share with you today, share with you guys, is a different approach to understand neural network training. Since the beginning of time, since everyone started to care about deep learning and started out with entering Coursera classes, we have been mostly focused about building a neural network and training it with an optimizer like an SGD or Adam. But but most of us really don't understand what is happening down there. What we understand is like our sole understanding is on the basis that we are trying to solve an optimization problem, and where we are trying to find a set of parameters for which we will get for which we'll get some a mapping between the input and the output spaces. That's the basic idea that we are having for some time. And this talk is all about sharing you a new perspective to look at deep learning training. And then I'll also share about an elementary idea of topology if anyone of you are not from math background or don't have any clue about topology. So I'll be sharing. So this talk will help you understand what topology is on a very high level. And the most important thing about topology is I think people have seen topology or have heard about topology by looking at Veritasium videos online on YouTube. But at the end of the day, we don't really have a good. So at the end of the day, we don't really have methods which can help us quantify. We are not aware of methods which can help quantify topology so that we can use topology for machine learning training. Since at the end of the day, a deep learning pipeline or a machine learning pipeline only understand numbers, right? So I'll be sharing you some ideas about how to quantify topology as a whole, how we can understand how each shape can be quantified into numbers, which we can then use for the deep learning training. And a basic idea about GANs. I think most of you in here have heard about GANs. So GANs are a really big deal since its inception in 2014, and they have seen a lot of they have been used in a lot of areas, including they're mostly famous about generating really high quality images. So I'll be sharing a basic elementary idea of GANs and all about the GAN training structure. And one of the most important question I would address in this talk, or I'm addressing with my research, is how why do GANs produce weird images? Since if anyone has seen any samples of GANs online, or if you go for thispersondoesn't exist.com, you can see you will see really great human images. But if you try to implement it on your own, you will see really bad images sometimes. For example, you can see an intersection between so if your data is of, let's say, multiple MNIST digits, you will see an intersection between 9 and 3 maybe. So those kind of images are really bad, and we don't really understand what causes these images. So topology will help us, give a brief idea about what's happening, why are these weird images being produced, and how topology explains weird images, and how can we exploit these topological properties to avoid, or at least try to avoid, these weird images. So that's my, so the last statement is basically my research topic or my research area, what I'm working on. So I think without further ado, we should start out with the first set of slides, topological spaces and neural nets. So, right. So before we start, I think I would like to give a basic recap about neural networks. So a neural network is basically a set of functions which tries to learn a mapping between the input and the output. But from a functional perspective, a neural network is basically a parametric map between input space and output space. What do I mean by parametric map? Is a map, or is a map is basically a function. So what I'm trying to do is trying to learn a set of parameters to map the inputs, to map between inputs and outputs. So if a neural network is basically a parametric map between the inputs and output spaces. In similar terms, given some input spaces, given some inputs and outputs, we try to find the best function which fits the input and output samples we have in our data set. And we do this by optimizing the parameters so as to minimize some loss function, which tells us how far uh, we are from the function. So how far we are from the function we desire to have. So that's one really crude way of talking about what neural networks are. So wait, I think I have not turned on my camera, right? Just wait a second. Yeah, I'm sorry. Okay. Uh, sure. Right. So we do this by so as I just mentioned, we try to learn these parameters by optimizing or so-called optimizing the parameters using an optimizer, and we try to learn a mapping between my input and outputs. The so if I have a function, if my neural network is basically a function f which is parameterized by theta, what I try to do is use gradient descent methods like an Adam or SGD, and I try to learn a mapping between theta, and I try to optimize theta, or I try to update the values of theta unless and until I get a direct map from input and output. So and at the end of the day, we hope to estimate the output and we hope to estimate the output space of f theta. So that's the thing that we are doing in neural networks from a functional perspective. But what we care about most in GANs is what we care about most in GAN is we have to understand what this output and input space is. We have been since this point of time, what I have seen, or what a lot of people do is basically mindlessly try to map the set of inputs to a set of outputs. But that's not what it's all about. We have to understand what this input and output shapes are. So with that, I would like to introduce the idea of topology. So what topology is basically topology is a study of shapes. And this is a really interesting field in mathematics, which have found a lot of implementation in studying astrophysics, in studying space, even in studying even in building paper folding origami structures. I think you guys know about that. And this kind of structures have been used for folding satellites so that they can be deployed in a much smaller place, and they can be deployed in orbit where they can spread out the solar panels where they can get the direct rays of sun. So topology has found a lot of areas of science. Topology has found its use in there, and the term might be a bit daunting. I think it was daunting for me when I started, but as I mentioned, it's just basically a mapping, or it's just basically a mapping from one thing to another, or basically a way of transforming one thing to another without tearing or without piercing any holes. So that's something which we have been doing in paper folding origami, as I mentioned. So if I want to create a swan out of paper, I'll just basically fold the papers in a way that this swan gets created. And but in case of neural networks, as I have already mentioned, we are not folding anything. In case of neural networks, we are mostly focused on something called the function, something called the input and output space, and we are mostly we just want to know what the shape of this input and output space is. And what do I mean by that is topology is an what I mean about that is instead of trying to understand, right, yeah, instead of trying to fold stuff, what we basically do is we try to deform stuff from one space to another, or we try to learn a continuous deformation from between two spaces. So for example, if I have so as you can see in this GIF here, we are trying to basically learn a mapping from a mug to a donut. So that can be seem a bit weird, but at the end of the day, if you look closely to the whole process, instead of tearing any holes, we are preserving the number of holes which we have. So, for example, here in this donut and coffee mug example, which have been used in topology for a long time, we are basically trying to preserve the hole, or trying to preserve the handle of this coffee mug, and then we are trying to deform it to form a donut. So that's one way of thinking about topology. And in deep neural networks, as you already know, that we don't have such a continuous space. What we have is basically samples from some space. So for example, what I mean by samples is, so for example, if you are trying to train a model using MNIST dataset, what you're trying to do is basically you take in around 60,000 samples from MNIST dataset, and what you do is kind of map that 60,000 samples to a number. Let's say a classification network. So we don't have that exact exact distribution. So we don't have that exact continuous shape which we have here. But what we have is basically shapes. So now a trivial question arises, like like in simple now the trivial question arises is how all these things relate to a neural network. Like why do we care about topology in neural networks? So there's this really cool idea which happens to be in deep learning literature. It's called Manifold Hypothesis. So this essentially bridges the gaps. This essentially bridges the gap between the this whole continuous space, this whole topological ideas into something which is much more usable by the neural network. So the idea is basically any high dimensional real world data lies on a low dimensional manifold embedded in high dimensional space. This sounds a bit weird. This sounds a bit critical, but we can highlight three important words here. The first word being high dimensional, the second word being low dimensional manifolds, and the third is being embedded. I'm sorry, I think I didn't highlight that part. Yeah. So right. So we basically have three different terms which we have to think about. So let's just break down this whole statement word by word. Right. So what we have is basically so what the theory states is every high dimensional real world data. And what do you mean by high dimensional is any real world data. For example, your photos, for example, your videos, your texts, or even let's say anything that you gather from the real world is basically high dimensional, since they constitute a lot of independent features, or which we call in deep learning literature the dimensions. So what do I mean by features is if I talk about this current video stream right now, as you can see my face, so there are a lot of things which there are a lot of features which kind of describe how my face looks like, or what the image which you're getting right now looks like. So that includes my glasses, my headphones, my lips, my eyes, all these kind of things kind of forms a feature, and which we in deep learning literature call the dimensions. And I think since most of you guys are from a machine learning background, you have a really great idea about what features and dimensions are. So instead of wasting much time on describing this whole idea, let's just move on to understanding how the whole thing relates. So conversely, each data sample is as you can see on the slides. So each data sample that we have is considered as a point basically. So for example, if you so let's just think for a moment, if among all the faces that we have in a photo, for example, if you Google search a human face, you will get thousands of different photos of humans, right? But all of those things can, instead of thinking of them as images, let's just think of them we turn the perspective of thinking of them as a simple data point from a certain distribution, or maybe drawn from certain high dimensional space. So what do I mean by that is, so there's a basic simple example which I can show in here is in case of MNIST data sets, like for example this three MNIST image that we have. If I'm trying to encode this MNIST image into a data point in a high dimensional space, So what I'm trying to do is I'm basically flattening it out to kind of form a 784 dimensional vectors, which is basically a data point on a 784 dimensional space, which is a huge space, and even for us humans is not easy to think about. We as humans can't think more than 3D. So let's just think that there is a space out there, on an abstract space which has 784 dimensions, and each dimension constitute one feature of this image. So that can be anything. So since we're flattening it out, these are just pixel values or pixel intensities at each point of the image. So instead of using this kind of 784 dimensional 784D images or 784 vectorization, we can also think about something much more meaningful. For example, as I mentioned, if as I mentioned that all my facial features, my headphones, my eyes, ears, and eyebrows, all those can form a single dimension instead of thinking about everything as a pixel. So we can kind of encode this information into a really high dimensional space. So in this case, it is 784D. So that's what high dimensional means in the whole statement, which manifold learning hypothesis says that every high dimensional real world data lies on some low dimensional manifolds. Now, coming to the second word, which is a low dimensional manifold part. So let's just step back for a minute and think of us as humans, or think of us as some dots living on the whole planet Earth. So as you can see here in this image, which I have added in here, we are basically some dots living on a surface of a sphere, right? So if I want to go from my place to, let's say, Europe, the shortest distance between my home and Europe is not a straight line. It's basically follows the latitudes and longitudes of the Earth. If I follow the lats and long of the Earth, I'll that would be the shortest distance instead of the direct straight line from my home to Europe. And that is the case of any different kind of shape. For example, even if I'm not talking about this spheres or Earth, even if I think about a donut, if you want to go let's think about a donut for a second, and if I want to go from one pole of a donut to the other pole, I really can't go in between the hole, right? Since the inside of the donut is a hollow part and that doesn't really exist, and that is not a part of the donut, what we can do is, instead of that, we traverse the surface of the donut, and that is my shortest path from one pole to the other. And same case, and the same idea boils down to the Earth. Like as I mentioned that we'll be traversing based on the lats and longs. So what? So this whole concept of this whole concept of shortest distance or shortest path on different shapes is basically boils down to something which we call manifolds. And manifolds are basically a shape which is locally Euclidean. So what do I mean by locally Euclidean is the distance between the distance between my face and my laptop right now is basically the shortest path is basically a straight line. But if my laptop would have been, let's say, 1,000 kilometers away, that would be a curved path along the surface of Earth. So that's a whole concept of manifold. And Euclidean, as I mentioned, Euclidean is basically a fancy word of saying the shortest distance is a straight line between 2 points. And what we want to delve into, and all these kind of spaces which are not Euclidean, which the shortest distance between them, which are not straight lines, those are called non-Euclidean spaces. And a manifold, as I mentioned, manifold is not directly non-Euclidean. It can be non-Euclidean on some way, like it can be globally non-Euclidean, but it has to be locally Euclidean. So what I mean by that is any 2 points which are very close together on a manifold or on a surface. So let me just walk back a bit. So if I have a manifold, or let's just say that I have a surface, and the shortest distance between those two surfaces is basically the shortest path. The shortest path between those two surfaces is basically a straight line between those 2 points. That can be that is a locally that is an Euclidean stuff. But if I try to move the 2 points away from each other, and I try to measure the shortest path, that is basic, and it follows a curved structure or any different structure that is not a straight line. So that kind of structures are basically called manifolds. And as an example, a bug on a ball surface, as I just mentioned. So now thinking about the manifold hypothesis, why is this important for us to study this manifold hypothesis? Like, why is this necessary? So there's a new way of thinking about deep learning on manifolds is a neural network. What it basically does, it tries to it gets a data from a highly non-Euclidean space. For example, the shortest path, or so for example, if I have a set of images, let's say image images, the shortest distance between those two image images might not be the straight line between them. It can follow any structure. We don't really know what that is. Since it lies in a really high dimensional plane, we can't really see what's going on in there. But what we can understand is the shortest that is a completely non-Euclidean space. And what a neural network basically does, it tries to stretches, squeeze, skew, and it does any kind of deformation on that space, and it tries to make those things linearly separable. So for example, in case of classifiers, so if I want to classify these two lines in this red and blue lines, as you can see, they are not straight lines, and the shortest distance between those two and a shortest distance between those 2 points on the red curve is not a straight line. So since this is a completely non-Euclidean example, so what a neural network does is basically it stretches and kind of skews the whole structure until it forms until those two structures are completely linearly separable. And a deep neural network basically in the hidden layers, what it does is stretches and skews everything. It stretches and skews the whole space until it can be classified by the last layer, which kind of creates a linearly separable unit. Which in case of classifiers, it tries to classify the two. It tries to separate those two things on two different domains. So that's a really a weird connection between neural networks and manifold hypothesis. So just coming back to the main topic about topology, like one of the things which we want to answer is why is this topology like, as you can see, topology has been governing this whole deep learning training process for a long time. And not just and any kind of neural network that you work on, that can be an LSTM, dense neural network, a convolution, whatever you try to work on is basically doing the same thing. So I think I'm not making the things too complicated, and it is really understandable that topology kind of is a really big deal in case of deep neural networks. So I would like to take some questions here before I proceed to the next part. So is there anyone who has any kind of doubts that I can help out with? Uh, does anyone have any doubts, or um, am I audible, or I'm not sure. Is there any doubt that I can help out with, or should I proceed to the next part?
I guess you should proceed.
Yeah, sure. Just give me a moment. Right. Yeah. So all this whole topological idea is really cool. Neural network is doing that and trying to squeeze stuff and stretch stuff. These are all really cool ideas. But why do we need to care about it? Since whatever topological stuff a neural network is already doing, why should we, why and how should we think of topology as an important thing in our work, and why how should topology influence the whole area of research? So before that, I would like to start out with the idea of quantifying topology, like how we understand topology as a whole. So as I mentioned that if you stretch, deform, skew, or whatever you do without tearing out the surface, that is basically topologically similar. But if I have a hole in it, or if I have any kind of disconnection in between the topology, that basically means that they are two completely those two structures are do not belong to the same topological class. And from there on I would like to share this idea of topological classifications. So so as you can see, holes are an important aspect of topology. And as I said earlier, a continuous deformation doesn't really count towards a change in topology. However, if I increase or decrease the number of holes on a surface, that is basically kind of that is basically kind of the differentiating point between two disconnected surfaces, or between two surfaces, or between two topological spaces. So those holes can be zero-dimensional holes, 1D, 2D, 3D, or whatever that can be the dimension of the hole is. So I think there was one really cool scene from Interstellar, I think. So so that dimensionality jump which that movie had was basically a four-dimensional hole which was trying to take a Cooper into a completely different dimension. So that's the kind of things which I'm talking about. So that's a four-dimensional hole. But in this scenario, let's just start out with the basics. And what we have is basically what in this slide. What I have basically is 1D, 2D, and 3D. 0D, 1D, and 2D holes. So in case of topology, there is this really fancy term which we use is called Betti numbers. Betti numbers are what which classifies holes. So Betti zero generally denotes the zero-dimensional holes. And what do I mean by zero-dimensional hole is basically the number of connected components. So for example, if I have one point that has that has Betti zero of 1, but if I have 2 points that would have a Betti zero of 2. So that means that I have two disconnected components in my space. So there goes the Betti zero structure. And next, if I come to circles, in case of circles, what I have is basically a hollow in between, which is just one ring. So I'm not sure if there is any laser point or something. Right. So okay. So what we have is in case of circles. So what the inside of the circle is basically one cycle, is basically the hollow part of a cycle. So in case of circles, as you can see, we can traverse this. So in case of circles, is basically a kind of a cycle. I think I'm repeating myself. I'm sorry. Right. So in case of but those that's what which classifies that's what which classifies the Betti one one-dimensional holes. Cycles are the things that count as one-dimensional holes. And in case of circle, we have Betti zero of 1 since there's only one connected component. And in case of 1D cycles, we have Betti 1, which is just 1 since there's just one cycle around the whole loop. Now coming to donuts, or coming to toruses, which we call it, which is the mathematical term for the shape of donut, we have Betti zero equals 1, which again just denotes the number of connected components we have. Betti 1 is basically the number of cycles. I don't think I don't think I have something which which sheds a more light onto it. But sure, I'll share with you guys at the end of the slides what how we can quantify, like what this Betti one number is for a torus. I'll share that at last. Right. So in case of Betti two, if you think of a torus, what we have in between is a void, right? So if I think of a hollow torus, not a donut actually, if I think of a hollow torus, what I basically have is a hollow in there. So that void counts as two-dimensional circles. So sorry, two-dimensional holes. So Betti two denotes the number of voids we have. And since torus is basically topologically similar to a mug, coffee mug, we have the same Betti numbers for torus and a coffee mug. But at the end of the day, what we can understand is that torus and coffee mug is basically are basically topologically similar. And this is how we quantify, this is how we classify between all the different kinds of topological structures that we have. We count the number of holes, we count the number of 0D holes that is connected components, 1D holes that is number of cycles, 2D holes is number of voids, and there are higher dimensional holes as well. But as of now, we don't really care about them much, since those are things which we can't visualize. So right. Okay. So I think I'll just go back to the last slide 1 second. Awesome. Right. So as what we can see from the previous slide is this concept of holes in any kind of continuous. This concept of holes is basically comes from any kind of continuous spaces. For example, as I showed in the previous slides, that we have a continuous structure. We have a continuous structure between 1 second. Yeah, we have a continuous structure which is a coffee mug. But in case of deep learning or in case of machine learning, we don't really have a continuous structure. What we have is just basically samples from that structure, or samples which are drawn from that structure. So how can we quantify holes, or how can we quantify the number of connected components which we have in case of such sparse samples which are not continuous? So here comes a really cool concept from topological data analysis. It's called persistent. Right, 1 second. Yeah, it's called persistent homology. What persistent homology is, the whole idea of persistent homology is a really simple concept of tracking the number of holes. So what do I mean by that is, so as you can see in this slide, what we are basically doing is we are trying to grow a small epsilon circles, or small circles around each data point, and growing it continuously till all the holes are filled. So what the basic idea is, the hole that closes the last will be the hole that is the most important feature. And other than that, all the holes that we track are basically noise, and we don't really care about them much. So what we what from a technical perspective, since this is just a 2D representation, from a technical perspective, if this point have been on a 3D, 4D, or let's say a 784 dimensional space, what we are basically doing is we are trying to grow something called epsilon balls, where epsilon is the radius, and we increase the radius of every epsilon ball in there, and whenever they come in contact with each other, we draw a straight line. And this whole thing of this drawing a straight line, or this whole concept of connecting to touching epsilon balls, is basically something which we call filtration process. And by filtration process, we kind of get an idea of what kind of holes what are the most important holes that we have. So for example, this sample that I have shown here is just some is just some data points that has been taken from a circular disk. So if I try to grow this persistent diagram, what I get is right. Uh, 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 if I try to grow this epsilon balls, what I actually get at the end of the day is the this things called persistent this things called barcodes. And what barcodes is, if you look closely, what barcode is basically is kind of tracking how long a hole survives, or how long does a hole lives from the moment it was created to the moment it ended. And as we can see that all the holes that we have, 0D, 1D, 2D holes, all are created at the beginning of the whole filtration process. So when we grow the epsilon balls, what we see is these holes are getting closed one by one. So that's exactly what we're keeping track of in this barcode visualization. So if you see at the top of the barcode, like if you I'm not sure if my mouse pointer is visible. Is my mouse pointer visible?
Yes, visible.
Right. So if you see at the top barcode here, it basically started at radius 0 and it ended at radius, let's say, 0.15. So the time that this hole lived is basically the difference between the starting and the ending point, the life of the hole. And what we care about most is a hole that lives longer. So that's the thing which stays persistent throughout the whole filtration process. And that's how we can quantify, or we can try and track the number of holes which we have in case of sparse samples which are not actually continuous shapes. So we can also represent this whole uh, filtration process, or we can represent this barcode in form of what we call is called persistent diagrams. In case of persistent diagrams, the idea is pretty similar. So in barcodes we have this 1D structure where we start drawing a line and ending it at a point where the hole died. In case of persistent diagrams, what we do is we use this as an x and y coordinate. So x coordinate is basically says the radius at which the hole is born, and y coordinate says the radius at which the hole died. So if you can see, the one of the most important holes that we have here is this is a zero hole which we have in here. So right. So this kind of gives us an idea of what kind of structures what kind of holes which we have from on a sparse sample space, like we have on this we get from a deep learning perspective. So apart from all this, like all of these ideas have been about topological, like quantifying topological ideas in a way so that it can be used for machine learning purposes. But like we but why are this necessary? Like why do we care about this whole problem as such? Like why are topological structures this much important in machine learning, and why should people care more about it? So me and my collaborator Simon Das, we have been working on a paper called Topo Sampler, a topology constrained noise sampling in GAN. It's basically it's basically it's basically a funky way of saying how we can improve the performance of GANs using topological methods. So if you would like to read the paper, or if you would like to go through the paper, or on Nudip's slides or anything, just scan this QR code if you want. I'll be sharing the slides at the end of the talk, so it will be easier for you guys to look into this. So before I move forward, I would like to take a short trip to the GAN land, like what GANs exactly are. So GANs are basically a game theoretic method for estimating probability density, as written on the slide. What do I mean by that is, in case of GANs, what we have is in case of GANs, what we have is something called generator, which you can basically think of as some kind of counterfeit, some kind of thief who is trying to generate counterfeit fake notes, and we have a discriminator who is basically trying to monitor who is basically trying to monitor the fake notes that are getting generated, and trying to understand and trying to classify between the fake notes and real notes. So if you think of it from a cat and mouse perspective, we have a thief who is trying to generate counterfeit notes, and we have police who is trying to detect those counterfeit notes. The police doesn't want the cop doesn't want the thief to succeed in making a best counterfeit note, and the thief doesn't want the cop to find out that it's a counterfeit note. So this is basically a cat and mouse problem. And by running this whole process for a really long time and improving the performance of the thief each and every time the cop detects the fake note, what we're basically doing is we're improving the thief as well as we're improving the cop. So at the end of the day, what we get is we get a thief who can generate really high quality fake notes. So if coming back to the machine learning land, if coming back to the machine learning land, in case of generator, we try to the generator basically can generate really high quality images by playing a game by playing a two-player zero-sum game with the discriminator. So as you can, all the images that you see in here are basically generated by a deep learning network who had no idea about what these things are, who or what the whole process is, or what or maybe they don't have any clue about dogs or cats or mushrooms or anything like that. So in short, GANs are really cool, but it sometimes takes the responsibility of giving us really bad nightmares. For example, this one. As you can see, we have a really bad. So the left image is supposed to be a baseball player who has somehow got intermingled with a hen, and the right image is an image of a hen which somehow got intermingled with the image of a baseball player. So that gives a really bad interpolation sample, or that creates really bad images of both the hen as well as the baseball player. So from a topological perspective, what does this basically mean? So most real world data comes from what we call is uh, most real world data having multiple classes. For example, the as you can see in this image, we have this classes 7 and 0, and that can be of any number of classes. For example, dogs and cats, or maybe any kind of images from what you get from Cypher 10 dataset or MNIST dataset, or any kind of classes. All these images basically comes from what we say is disconnected distributions. So what that means is that we can interpolate between sevens. That would be totally fine, but there is no direct crossbreed between 7 and 0. Like there is no direct way of going between 7 and 0. Like there is no possible way a 7 can ever turn into a 0. So this kind of scenarios of having two disconnected distributions, or two disconnected manifolds, as we say, we really can't have a we really can't use sorry, my bad. So what GANs basically do is they try to kind of learn the intermingled thing between these two distributions. And the weird samples which you have seen basically comes from the central part, like the point between these two disconnected manifolds. So, for example, 7 and 0, which we have, the bad sample, as we can see here, comes from in between 7 and 0. And why does this happen? Like, why does GANs work like this? So, what GANs basically do is they try to learn a globally connected cover over the two disconnected surfaces, over two disconnected distributions or two disconnected surfaces. So, as you can see in the blue, as you can see in the blue part of the image, the blue image is the blue image basically says what what kind of distribution we have in the data. So, for example, one of the components of this blue image can be thought of as an image of a cat, and the other component can be thought of an image of a porcupine. So, but the what GANs learn is is they learn a globally connected cover over it. So the red part which you see in here, that's what a GAN is learning. A GAN is learning a globally connected cover which doesn't at all model this disconnectedness. So that is what causing the whole issue. That is what causing the whole trouble. And the weird samples which you have, which you see, comes from this connected part, which is not supposed to be connected. Right. Now, that's our problem statement, and that's how that's what we're trying to tackle. And there has been a lot of works in this area. Like, there was this 2018 newspaper which studied this whole problem by using different generators for or using different generators for modeling each part of the distribution. So, on a simpler term, what I mean is they're using different thieves to understand to build different kinds of nodes. So, one thief is trying to build one thief is trying to counterfeit 10 rupee note. The other thief is trying to counterfeit 200 rupee note. So one thief doesn't is not responsible for learning, or one thief is not responsible for building the both these nodes. So in such a way, so once we allot these generators to each of these disconnected components, they learn each disconnected component, which is itself a continuous part, and that which is not and each component is a connected component in itself. So as a result, the generator which is learning this kind of components kind of uh, they, they don't care about this disconnected part. So as a result, when we try to generate samples from it, as you can see on the third image from as you can see on the rightmost image, what happens is they generate samples which they each generate samples which do not have any which do not which kind of models this whole disconnected components thing. And the middle one which you are seeing is the state of the art GAN, which we call the Wasserstein GAN. That is the kind of Wasserstein GAN is learning a globally connected circle over this whole disconnected part, and it's not modeling the and it's not modeling that disconnectedness. And another but that's one really important problem is why is this important to revisit this whole problem. This looks like a solution, right? But at the end of the day, as you can see, since we are using multiple generators, and sometimes we don't even know how many classes of data are there, and how many classes are not and how many classes lies on different manifolds, or how many classes have different distributions. We don't really understand this whole geometry of the high dimensional space without actually trying to use some kind of without actually introducing some topological perspective to it. So as a result, uh, at the end of the day, we can land on something which we call the too many generators. So we will have a so for example, if we have around 10 different disconnected distributions, what happens is I have 10 different generators to train. And training a GAN is kind of is a really hard problem, since modeling a whole cat and mouse problem is not always optimal. So as a result, training multiple of the generator can be a really huge nightmare. And that's how we can so there was the hard to train part. And most important, which you can see, is running one GAN or trying to draw samples from one GAN is hard. Obviously, there are multiple millions of parameters in each generator. But if I try to do it from multiple of the generator, what happens is we have a really slow inference pipeline. So, for example, if I want to generate one sample, we kind of have to run all the 10 generators at the same time, and we kind of end up with a overflow error in our GPUs, which is not something which we want. So another approach which was proposed in this recent ICML proceedings by in ICML 2020 was this whole idea of rejection sampling. The idea is pretty similar. Like we use it, so the idea is pretty similar. Like we use a generator, or we use a continuous generator to model the whole process as well as the middle part, and then we use some kind of weird mathematical structure to understand which parts do not lie on the distribution, and we remove those samples. This idea is pretty straightforward, and the authors have made it into the ICML, which is a really big deal in machine learning conferences. So this was a really cool idea which they have worked on, and the same author have and the same author have also made an ICLR submission, which is another big deal conference in machine learning, where they kind of where they propose a different approach, but they end up with the same process of removing samples which are not required. So that's a really cool way of solving this problem, but it still has some drawbacks. For example, let's just start out with the first one. So if we consider the number of usable samples over if we consider the number of usable samples which we can use, for example, in case of the image that I showed earlier, this one, if what happens is if I remove these samples from my generator output, we have to sample a lot of times to get what we desire. So what do I mean by that is if when I do a forward pass in a generator, what I get is a mixture of good samples and bad samples, right? And if I devise an algorithm which removes these bad samples, and I want to get and I want the generator to be precise, to have the really sharp precision to understand to model this whole data. What happens at the end is that the precision decreases. So that kind of is not what we desire, since precision is defined by the number of samples which we had and the number of samples that are usable. So, for example, if I want around 100 good samples, I don't know how many times I have to sample, right? Like maybe I have to sample 1,000 times, maybe I have to sample 2,000 times. There is no upper bound to that, how many times I have to sample. And everything boils down to hoping that we will get good samples. And right, and again it's computation intensive, since we have to sample the whole generator multiple times, and we have to do the forward process multiple times to get the result, which is not something which we want. So which kind of increases the computational complexity as well, and which is not which is again a negative point towards this whole process. And the third part, which is called the generalization assumption. So I would like to take a little bit of short detour from the whole idea of topology and go and give a small and a small brief about what do I mean by the word generalization. So we define generalization as a capability of a neural network to learn something that is useful instead of just mugging the whole data set up. So this, I think you guys have tried. I think you guys have trained basic MNIST classifiers or ciphertext classifiers. But at the end of the day, what we end up seeing is the generator or the neural network kind of memorizes what it sees. There was a really cool paper in 2017 by Zhang et al., which kind of demonstrates this whole problem that a neural network that a neural network memorizes more than it learns. So this problem of generalization, in theory, can be tested very easily by doing something which we by perturbing the input by a small amount. So what do I mean by that is, if for a function, if let's say a mathematical function, if we change the input by a slight amount, let's say a small amount epsilon, we don't expect a really huge change at the output, right? So if we see a really huge change in the output, that basically means that the function is not well modeled. So what happens is this is kind of a symbol which says that that the function has not generalized. So if I make a slight change in the input of my neural network, and I see a small change in the output of my neural network, that's what uh, in such a scenario we call it a strongly generalized neural network. And that is something that assumption that is the assumption which the authors took in this approach, that they propose an algorithm which basically perturbs the input, or which basically adds a small amount of noise to the input, and whenever they see a huge amount of change, they reject that sample. So what if what if the generator that we are learning, or what if the GAN that we are training is not generalizing well, and is solely reliant on memorizing the whole data set up. So in that scenario, this method will not perform well at all. So there goes a negative parts of this whole project. But drawing from this idea of how the whole thing works, me and my colleague has been working on this really cool idea, which I think you guys can relate. Which I think you guys can relate if you remember the whole part about the Betty numbers. Right. What we generally do is, instead of modeling, or instead of removing samples which you don't need, or instead of using multiple generators, we model each disconnected component. So for example, each of these disconnected components, we model the interior part of it as zero dimensional holes. What I mean by that is the internal part of the the, the disconnected parts of the whole manifold. It can be modeled as zero dimensional whole, or as Betty numbers. If you remember from the previous slides, what we have is, I think I have to go a long way before that. Uh, I'm sorry. Was it? Right. So if you can see in here, what Betty zero basically does is basically counts the number of disconnected components we have. So if I can model this disconnectedness in terms of Betty zero, that would be then it would bring the whole problem of disconnected manifold learning, or disconnected learning of the generator, to a topological way of thinking. So what in our work, what we did is, we used the one second. Right. So what we did is, we modeled this whole. Uh, we thought of this whole disconnectedness as a zero dimensional holes, and we minimized something which is called the topological signature loss, borrowed from a previous work by Michael Moore on topological autoencoders. What we did is, we used that loss function, which basically quantifies the topology in terms of uh, yeah, which basically quantifies the topology using persistent homology. So what it does is, it kind of enforces. We use this as a loss function, so that the holes get explicitly fed into the neural network, and the neural network, instead of learning this whole process, or trying to learn a globally connected cover, it can focus on how to minimize the loss by introducing holes into the data manifold. That was a basic idea which we started out with. So for that, we introduced a novel architecture, or we introduced an architecture which basically tries to model this whole, uh, which tries to model this whole introducing part by kind of separating this out from the generator module. So we have a generator, obviously, but other than that, we have our small neural network, which basically introduces the whole at first. Then we use a generator, and we use a generator to kind of stretch, squeeze all these disconnected components all together, so that we get what so that the we get the whole so that we get the final posterior. And what I mean by the posterior is basically the output of a generator. So what happens is, once we model the holes, and once we use a generator to stretch, squeeze each of these discrete components without changing the topology, we are supposed to end up at a plane which has a required number of discrete components, or any kind of d-dimensional holes. That can be 0D, 1D, 2D. So kind of generalizing the whole idea of holes in topology into very high dimensional spaces. So this was a proposed architecture which we proposed. But one of the most important things you should notice in this whole process is, this is not working as we have thought. So as you can see, the generator kind of fails to understand what's happening in there, or kind of is not creating a Dirac onto the samples. Instead it is jumping around the whole sample space and creating really shitty samples, as you can see. And right, we also are facing mode collapse. What does mode collapse mean? Is basically all the inputs, all the samples generated by the generator will be the same sample. So for example, if a generator is supposed to generate samples that are diverse in nature, but what we end up with are samples that belong from the same class. And right, we have tried a lot of things to try to improve this problem, but we really can't seem to improve it anyways. So, but we did take away some really cool ideas which helped us moving forward with the research. uh, One of the things which we noticed is instead, so when we try to model this whole problem in terms of in terms of topological regularization, instead of creating new holes, what we are basically doing, we are stretching the manifold, or we are stretching that continuous surface and not tearing it. And that kind of made me remember why it's called continuous deformation. So that kind of helped us focus on that we can't use a neural network to introduce new holes, and that would be a part of our next paper, which we'll be working on. And that's a really cool way of so here is a visualization which we got from this whole process. That, as you can see, we try to model disconnected distributions like the one on the top right. We try to model this kind of distribution using a continuous prior. What happened is, we instead of creating something new, what we did is we basically stretch it out, and that is not something that is useful, since we are not creating any holes in the manifold. And again, we use the GANs, but in case of GANs, we did make some assertions about the homeomorphic nature. Homeomorphism is a fancy term for saying that the thing stays on the same topological object, so it will not introduce any holes. So what we did is basically created some what we did is basically asserted some guarantees that a generator will never be able to create a new holes onto the manifold, and that is something which helped us get into NeurIPS this year. And right, so these are the main contributions which we worked on. We proposed a topological perspective of viewing the discrete manifold learning in GANs. We showed some empirical evidences that the prior space topology kind of influences what we learn at the end. We also propose a systemic method for enforcing topological constants, and we also empirically prove that the homeomorphic guarantees for the for a Lipschitz constant generator, which is a fancy term for saying a generator which learns homeomorphisms. And for the conclusion of this talk, what this is what are the things that we talked about. We proposed a topological perspective of viewing discrete manifold learning in GANs. We show empirical evidences on importance of price space topology on discrete. I think this is the 1 second. I'm sorry. So this is a talk from the last part. Sorry. Right. As a conclusion for this talk, I would. So we saw how topology kind of influences neural network training, and how they can be useful in the whole learning process. We Topological data analysis, which I have been talking about, is a really emerging field, and there are not much work in this domain. So if anyone wants to hop on to machine learning research, I would definitely suggest go for anything which is related to topology or geometry. So that is a really heating up topic in this current research areas, and you can make a really and whatever contribution you will make, that will be really valuable in the academia. So yeah, you will get a really so whatever paper you write, any good contribution, any contribution will be a good contribution. And manifold learning hypothesis, which I mentioned before, is something which helps bridge the gap between topology and neural networks. And this is something which has been studied for a really long time. And this is still an hypothesis, since no one has ever to prove it yet. There are no theoretical guarantees on it, but based on the experiments, or based on the empirical evidences that we saw in our experiments, or in any other experiments that the authors saw, is basically that this idea holds, that any real world data lies on a low dimensional manifold. And right, new frontiers in theory. And what another thing which I think I should have included in the slide is this topological perspective is also bringing in some new ideas in constraint optimization. So what I mean by that is, if what I mean by that is, so for example, in a self-driving car, we don't want a car which gives any kind of probability towards hitting, which gives around even if a low probability towards hitting passerby for going on the road. Those are the things that we want to avoid, and topology is helping us to bring in much more interpretability toward this whole process, so that we can explicitly specify that do not hit someone who is crossing the zebra crossing. So that is something topology is helping us doing right now. And I think it will be very useful if I think it will be very useful if more people come into this research field and work with us or work with all the people who are and work with the other really famous people working from Stanford and MIT. You guys will, I think those guys will really appreciate if you can work in this area. And yeah, thanks for your time. And I would like to receive some questions if you have any or anything that you want to ask. Even if you want to ask about how to start out with this area, I will be happy to take some questions. Uh, uh, so are there any questions about it or anything that you want me to revisit or anything that you would need help to start out with? I'll be you can reach out to me or you know if you have anything right now to ask, feel free. Shorjo Podar, can you unmute yourself and ask? It would be easier for me, I think. Shorjo, hello. I can't hear you. Can you speak up? I still can't hear you. Is there anyone else who would like to ask a question? Shorjo, you can drop it in the chat if you have any questions. All right. So just drop it in the chat. I think that would be great. Hmm. Is there anyone else who have any questions regarding even not just regarding the slides or anything that you would like to like my help in machine learning research or anything you want to understand about it? Like that can be that can be a part of any machine learning project you're working on or anything else related to machine learning. Just feel free to ask me or even reach out to me on you can find me on captainpool.me. Yeah, you can I'll just share my screen. I think that would be better. Yeah, you guys can find me here, and if you want to have any if you have any questions, feel free to ask me via email. I have my email LinkedIn here, or even you can if you can reach out to me on LinkedIn. Right. So your question is you are not from a CS background, and you did a course on Coursera but couldn't understand most of it. Right. So yeah, that was something that I faced also initially. in this kind of talks, but I think it would be helpful since DSC TIU is probably recording the talk, so you can visit it later. So, but for starting out, I would suggest going through some tutorials at first. And so this year, NeurIPS conference has opened all the slides which they have. I think you can find it on. I think you can find it here. Just take a visit in there, and you can find a lot of the talks about this topological stuff or anything that you need, or even if not topological, you can read up or see some really famous people talk about or give tutorials about reinforcement learning, deep learning, computer vision, or anything else. So just feel free to visit the site and you can see the talks there. They're also available on Slides Live, but I'm not sure what's the handle which they're using this year. So 1 second, I'll just give a check. I think. Oh yeah, got it. This is, I think this is from last year. Yeah, right. You can also see some talks here. You can see some tutorials here. So maybe that would be helpful. Anyone else? Does anyone else have any questions that I can take? So I think that's it for today, or that's it what I had to say. So thank you guys for joining. Or if you guys have any more questions, feel free to reach out to me on LinkedIn, on email, or anything else that you prefer. Or yeah, and
Okay,
I
so
have shared my website on chat, so maybe you can visit there.
okay, so thanks Adrishda for taking this session.
Sure.
And I guess that's a wrap for today. So yeah, see you all next time.